You know, whenever you dissolve something, like salt in water or sugar in your coffee, you probably don't think much about it. But there's this incredible hidden world of energy happening right in that cup. Today, we're going to dive in and unpack the science behind it all, the thermodynamics of solutions. So, what's the deal with that? How does a cold pack suddenly get freezing just by squishing it? Or how can mixing two things together get hot? It's not magic, it's just really, really cool chemistry. And the answer to both those questions has to do with something called the enthalpy of solution. Take a look at this. Dissolving something isn't just one single event. It's actually more like an energy journey. You've got your starting ingredients, right? And to get to the final solution, there's this constant push and pull. Some parts of the process need you to put energy in, while other parts actually release energy. So let's really get into this energy tug of war. The entire process, believe it or not, can be broken down into 3 totally distinct steps. And each one has its own energy cost or its own energy payoff. Okay, let's get the official definition out of the way. The enthalpy of solution, you'll see it written as delta H sol, is simply the total amount of heat that gets absorbed or released when 1 mole of a substance dissolves completely. It's basically the final score of that whole energy journey we were just talking about. And this right here, this lays out the battle perfectly. First, you have to spend some energy to break apart the solute particles. Think of it like you're physically prying apart little salt crystals. That costs energy. Second, you also have to spend energy to push the water molecules apart to make some room. So those are your energy investments. But then, step 3 is the big payoff. New bonds form between the salt and the water, and that process releases a bunch of energy. And here's what determines the outcome. If it costs you more energy to break all those old bonds than you get back from forming the new ones, well, the whole thing has to pull in heat from its surroundings, and that's why it feels cold. That's an endothermic process. That's your instant cold pack. But if that energy payoff is bigger than what you spent, the process releases extra heat and it feels hot. We call that exothermic. So we know there's a total heat change going on, but it turns out there are 2 really important ways we can measure it, and they give us totally different kinds of information. You've got the big picture view, and then you've got the single moment snapshot. First up, we have the integral enthalpy of solution. Just think of this as the grand total. It's the overall heat change you get when you dissolve a certain amount of stuff. It's the final result of that whole energy tug of war. And then there's the other one, the differential enthalpy. Now this one isn't the total, it's the instantaneous heat change. It answers a very specific question. At this exact concentration, right now, what's the energy effect of adding just one more tiny particle? I absolutely love this analogy because it just makes the difference crystal clear. The integral enthalpy is like your overall GPA. It's the cumulative result of everything you've done so far. But the differential enthalpy, that's like your grade on the very next assignment. It's the immediate impact, right now. Both are super important, but they tell you very different things.
So if one is the total and the other is just the instantaneous change, how in the world do they connect? Well, it turns out there's a really elegant relationship between them, both mathematically and graphically.
All right, let's check out this curve. On the vertical axis, you've got the integral enthalpy. That's our GPA. And on the horizontal axis, you have the concentration. You can see right away that as the solution gets more concentrated, the overall heat effect changes. And importantly, it is not a straight line. And here is where the magic happens. This is how they connect. If you want to find the differential enthalpy, your grade on that next quiz, at any specific concentration, all you have to do is find that point on the curve and draw a tangent line to it. The slope of that line is the differential enthalpy at that exact moment. How cool is that? And hey, don't just take my word for it, the source material puts it perfectly. So the really crucial takeaway here is that the differential enthalpy is just the rate of change of the integral enthalpy. They are fundamentally locked together. All right, that's enough theory for now. Let's get our hands dirty and see how this actually works in practice with a couple of quick calculations from our source notes. Okay, problem number 1. We're dissolving 2 moles of potassium nitrate, and in the process, 10 kilojoules of heat are absorbed. That little plus sign tells us it's endothermic. It got cold. So what's the integral enthalpy? Luckily, the math here is pretty straightforward. The integral enthalpy is just the total heat change, which we call Q, divided by the number of moles, N. So we just take our positive 10 kilojoules and we divide it by the 2 moles that we dissolved. And there you have it. The integral enthalpy of solution for this process is plus 5 kilojoules per mole. Easy enough? Now for problem 2. Pay close attention to the wording here. At a certain concentration, we add a tiny amount, just 0.02 moles, and it releases 0.6 kilojoules of heat. That's a huge clue that we're looking for the differential enthalpy, that instantaneous change. So for this one, the formula is the change in heat over the small change in moles. Now, since the heat was released, our change is actually negative 0.6 kilojoules. We're going to divide that by the tiny amount of moles we added, which was 0.02. And that gives us our final answer, negative 30 kilojoules per mole. That negative sign is our confirmation that, yes, at that very specific moment, the process was exothermic. So, let's just end with this thought. The idea that the energy landscape of something as simple as a solution is constantly shifting with every single tiny particle you add, that's just fascinating. It really shows that even in a plain old glass of salt water, there's a dynamic, powerful, and totally invisible world of thermodynamics going on.